All right, in this lesson for 2.5, we're doing linear inequalities, so we're going to graph them on an xy axis, just like we graphed our lines. So linear functions form the basis for linear inequalities. A linear inequality in two variables uses the inequality symbols of less than, greater than, less than or equal to, greater than or equal to, and there's one more inequality symbol. We won't be using it today, but it is an equal or not equal to. All right, its graph is a region. It's going to cut it in half. So the graph is a region of the coordinate plane bounded by a line. And the line is considered a boundary line. And it's going to divide it into two sections or two regions. Now, one of the things I want to remind you of is when we go to graph these, we are going to use different things. So whenever you go to graph and it's less than or greater than, you are going to use a dashed line, and you have to remember that you're going to shade. Whenever it is less than or equal to, greater than or equal to, you're going to use a solid line. And again, don't forget to shade the graph. All right, so here we go. I already have y equals mx plus b. That's the form we want this in. So we need to think about our slope is -1/2, and our y-intercept is +1. So this takes us right back to 2.3. We're going to plot our y-intercept at 0, 1 right here on the y-axis. Make sure you find your y-axis. And then I'm going to go down 1 and right 2 to cover my slope. So -1, +2. Now, don't forget that this is a dashed line. So sketch in your dashed line as best you can. And make sure you fill up the graph, because eventually we're going to graph systems of inequalities, so we want to make sure we can look at the whole graph. The next thing we have to do is decide how to shade. And so there's two ways of looking at shading. If I look at this and I see that y is less than the line, reading it as y is less than the line, look at your y-axis, not your x-axis. It's saying y. Look at my y-axis. As I have my line cutting the y-axis in half, as I go up, the y is getting bigger. As I go down, the y is getting smaller. So if my problem says y is less than the line, y is getting smaller as I go down. So that's going to allow me to shade this half of the graph. So there's my shaded region. So I can use my y-axis as a number line, greater, less than. If you don't like that, you can go back to your test points that you've done before. And the easiest test point is 0, 0. So if I'm comfortable shading, I don't need to use a test point. If I want to double check myself, go ahead and use that test point of 0, 0. The only time I can't use it if it's on the line. But if my test point works, then everything works. If my test point fails, then it must be the other side. So take 0, 0, plug it in. 0 is less than -1/2 times 0 plus 1. 0 is less than 1. 0 is less than 1, that's true, so then I shade everything over there. All right, when I look at my next one, we need to determine what the slope is and what the y-intercept is. So looking at this, some of us know that we can look right at this and know this is going to be a horizontal line. The slope is 0. We can rewrite it as y is greater than or equal to 0x plus 2. So my slope is 0, my y-intercept is 2. I like to look at this and say it cuts through the y-axis at 2. So here is a solid line because it's allowed to be equal to. Here's my solid line. And again, y is greater than. So if I look at my y-axis, as I go up, it's greater. So I'm going to go ahead and shade this top region. If you want to use a test point because you're more comfortable with that, again, I'm going to use 0, 0. But notice there's nowhere to put the x. So it's just y is 0 greater than or equal to 2. And that's not true. Y is not greater than 2. So if this point doesn't work, then nothing works, and I shade everything above it. All right, looking at our next example, this is in standard form, and the directions just say to graph it. So most of us want to solve this for y equals mx plus b. So go ahead and take a minute and solve that for y. So first I'm going to subtract the 3x. and I get negative 4y is less than negative 3x plus 12. Now that I have that, I'm going to divide each piece by a negative 4. And that's exactly where we need to take a pause and remember that we need to flip our inequality. So make a little note of that. If you multiply or divide by a negative number, flip your inequality. And the reason we're flipping that inequality is because we are changing the rules. If you look at this as a mirror image, as I increase and I decrease, so we're flipping from a 5 being the highest to a negative 5 being lower on the negative side. All right, so what's your negatives? We get a positive 3/4 x, and we get a negative 3. So that's the equation I want to focus on. And I actually want to draw attention to this because I want to make sure I use the right sign. So y-intercept is at negative 3. So plot that down here at 0, negative 3. And then I'm going to rise 1, 2, 3, run 4. And there's my point. Dashed or solid line. Go back to your inequality. It's not equal to, so dashed. And then take a minute and decide where to shade. So again, two theories on shading. Here's my line, y is greater. I don't want to go back up here. I want to use my final answer. Y is greater. If I look at my line, y is greater as I go up. So I'm going to shade the upper half of this region. Now, if I want to use a test point again, I'm going to stick with 0, 0. And I'm going to go back to the original. So 0 minus 0 is less than 12. 0 is indeed less than 12. So that 0, 0 works, and so does everything else. Okay, so now we have this one. There is no y here. So that should stand out to us. Second, I'm not a fan of the way it's written. So I can tell you right now, since there's no y, this is a vertical line. And as we've talked about, the slope of a vertical line is undefined. So yes, it's going to cut through the x-axis at negative 4. And it would be a dashed line here. So there's my dashed line. But here's my problem. If I read it as a greater than symbol, I'm likely to shade greater than and get it wrong. You always need to read it from the variable. So I think it's worth the time to rewrite it as x is less than negative 4. I'm not flipping the symbol, but if negative 4 is bigger than x, then x must be less than negative 4. So x is less than negative 4, and now I am looking at the x-axis, and this is where I would shade. The next set of examples we have, we're asked to graph using intercepts. So the minute they ask me to use intercepts, we are talking about the x-intercept and the y-intercept. It's very important that you don't just solve for y equals mx plus b and graph. We'll get the same graph, but you did not use the right technique. So when I'm talking about the x-intercept, there are two facts I need to know. One is it crosses the x-axis. And if I know it's on the x-axis, then I know the y value is always 0. So to get full credit, you need to list your x-intercept as an ordered pair. And the reason I'm pushing that is so we understand where these numbers come from and how we can use them later. So we're laying this out for our future math use. So I'm going to put that 0 in for y. 2 times x plus 3 times 0 is greater than or equal to 6. That's going to cancel itself out. That's why we like the intercepts. And I get 2x is greater than or equal to 6. And so I'm going to solve this like an inequality. If I multiply or divide by negative, I'd flip the sign. So here it is, x is greater than or equal to 3. So my x-intercept is this point at 3, 0. But I'm going to take it one step further. See how this says x is greater than or equal to 3? If I'm looking at my number line, wouldn't I shade that way? If I'm looking x is greater than or equal to 3, I would shade to the right. And I'm going to leave that little arrow there. It's going to help me in the end. Okay, y-intercept is on the y-axis, and that means the x value is always 0. So here we go. Let's plug it in. 2 times x is 0 plus 3y is greater than or equal to 6. That's gone, and I get 3y is greater than or equal to 6. and I divide by 3, and I get y is greater than or equal to 2. So let's plot that point at 0, 2. Now take one more second. It said y was greater than or equal to 2. So I would look at this and I'd be looking up because that's where y is greater than or equal to 2. Solid line because it's equal. So drawing a nice solid line here. And do you notice that both the x pointed to this side of the region and the y pointed to this side of the region? So as long as I've done my inequalities right, I already know where to shade. So by solving for my x-intercept and my y-intercept and keeping my inequality, I can see where to shade. You cannot go back and look at this and say, oh, it's greater than, I shade greater. Because if this was a negative number, we would have flipped the sign. So you either have to shade using your x and y intercept technique or, again, a test point. And I'm going to use that 0, 0 every time I can. So I plug in 0, I plug in the 0, and I get greater than or equal to 6. 0 is not greater than or equal to 6. So I don't shade here, I shade the upper half. All right, same thing using intercepts again. So the x-intercept is an ordered pair. Put my 0 in. Y-intercept is an ordered pair. Put my 0 in for x. That should guide you through the process. All right, here we go. 0 goes in, so I really have 3x plus 4 times 0 is less than or equal to 12. So that's gone. And some of you might shortcut that, and that's fine, that you don't have to write it all out, but show some work. X is less than or equal to 4. So here is my ordered pair to get full credit, and here it is on the graph at 4, 0. It said x is less than or equal to 4, so I'd be coming down away from 4, down to the left. Plugging in my 0 for the x value gives me the y-intercept. That's gone. I have 4y is less than or equal to 12. Divide both sides by 4, and I have y is less than or equal to 3. Again, if we had a negative, we would be flipping that sign if we were dividing by a negative. So my y-intercept is 0, 3. And take that quick second. Y is less than or equal to 3 would be coming down. Determine if it's dashed or solid. It can be equal to, so it's going to be a solid line. There you go. And then if we think about the shading, both of these shaded this direction. So if we do it right, they should be going in the same region. Again, here a test point of 0, 0. If you're comfortable shading by using this, you don't have to do the test point, but it's a nice check. If you're not comfortable doing this, use the test point. So plug in your 0, plug in your 0. 0 is less than or equal to 12. That is true, and that's why I shaded 0, 0 and everything else with it. The next examples don't tell us that we need to use x and y intercepts or y equals mx plus b, so I'm going to go ahead and do what most people are probably comfortable with and do y equals mx plus b. Now you have two options here. Option 1 is distribute that 2/3, and I'd actually like to not distribute it. I'd like to make you look at it a different way. Since everything on this side is multiplied by 2/3, I could divide by 2/3 to get rid of it. But we don't divide by fractions, we multiply by the reciprocal. So that'd be 6 over 6, or 1, since they cancel out. And I multiplied this side by 3/2 again. So I am left with 2x minus y is less than, my 2's are going to cancel, and I'm left with 3. So that was actually a nice way of getting rid of my fraction. It worked out. So I'm going to go ahead and solve for y by subtracting the 2x. I have negative y is less than negative 2x plus 3. Now when we come in here, we have to divide everything by a negative 1, and that is going to cause me to flip my inequality. I end up with a positive 2x and a negative 3. So here is the inequality I want to focus on when I graph, starting with my y-intercept at negative 3, so 0, negative 3. And then I'm going to do a positive 2 over 1. So up 2, run 1. Rise 2, run 1. I want an accurate graph, so I'll do a couple points. Dashed or solid, you have to decide. This not equal to, so it is going to be a dashed line. If you forget, erase. If you're using pen, you better write the word dashed beside it to clarify. And then looking at this, it says y is greater. So here is my line, y is greater as I go up the y-axis. Again, if I want to use a test point, I would continue to use 0, 0 as long as it's not on the line. In this next problem, same idea. We could distribute the 2, or we could divide out by 2. So I am choosing to divide both sides by 2 to cancel that out. I get 3x minus 4y is greater than 12. At this point, I can use x and y intercepts, or I can solve for y equals mx plus b. I'm going to go ahead and use x and y intercepts just to practice that. So the x-intercept is an ordered pair, the y value being 0. So 3x minus 4 times 0 is greater than 12. So that's going to cancel. 3x is greater than 12. X is greater than 4. So here's my ordered pair at 4, 0. And if x is greater than 4, I'm going to shade to the right. Using my y-intercept rules, I have it as 0, and then I need to find that y value. So looking for that y value, see if it gets a little better there. Looking for that y value, I plug the 0 in for x, keep that minus 4y is greater than 12, and that cancels out, but I have a negative 4y is greater than 12. So when I go to divide by a negative, I flip my sign, I get y is less than negative 3. And so I put that in there also. So here is my point at 0, negative 3. And y is less than would be shading going down. Now if we come back, the inequality was a greater than symbol, but it's not equal to. So I would be drawing in this dashed line. And by my x and y intercept number line idea, my shading should be this lower region. So where I want you to be careful, and why I thought this was a good example to use x and y intercepts on, is if I go back to the original or to here and I see greater, so I think shade above the line, I'm going to get it wrong. Because if I would have solved this for y equals mx plus b, I would have had it as a positive slope. So if I would have done y equals mx plus b, I would have had a positive y, but I would have had to flip my sign because I would have had a negative 3 divided by negative 4. So I'd have a positive 3/4 x, and I would have a negative 3 here. And see, that less than symbol is what I'd want to focus on. So you cannot use the original inequality symbol when you're graphing using x and y intercepts. You want to look for these, or again, use a test point of 0, 0. And so if I put 0 in here, or in the original, I get 0 overall is greater than 24, which is not true. And so that's why I won't shade this half of the graph, I'm going to shade the other half. In our last example, we're going to do a word problem. And the best way to do a word problem is to lie everything out, see what we're looking at, and then start attacking it. So it's going to be a linear inequality. And we're talking about a theater. They're going to charge $7.50 for adult tickets and $5 for discount tickets. The theater needs to make at least, now catch that, it says at least $240. That's how it's an inequality. They want to make at least $240. So $240 would cover the cost. If I make more than, or they make more than $240, that's going to be good. So $240 or more. Now, here's the question, and this word problem will always lead you to your variables. It says, how many of each type? There it is. How many of each type of ticket must be sold to make a profit? So, if 20 discount tickets are sold, how many adult tickets must be sold? Create an inequality that represents the situation. Solve the problem by graphing. Okay, I'm going to let this sit here. This, if 20 discount tickets are sold, how many adult tickets must be sold? This is like a second part. So I'm going to do this second, and I'm going to start here. So first it says how many of each type of ticket. So I'm going to stick with using X and Y because I'm graphing. So having it as an X and Y is great for graphing, but maybe you would use A for the number of adult tickets and D for the number of discounts. But because of the graph, we want to do it this way. And also note that you have to watch which way you define them, because neither of these variables is truly the dependent variable. So X is the amount or number of adult tickets. And so I have all my information together. I'm going to write down that each adult ticket is $7.50. All right, and then Y is the amount of discounted tickets. And each discounted ticket is $5. So it's really important that we define our variables. We're going to use that to help us with our graph. We're going to use it to help understanding our answers. So if you think about this, the money raised for adult tickets plus the money raised for discounted tickets is what we're looking for, and that money has to be greater than or equal to $240. So the money raised by selling adult tickets and the money raised by discounted tickets has to be $240 or more. Okay, so that's what we're looking to cover. So whenever I go to do this, let's think about an equation. Each adult ticket is $7.50, so that's the cost times the quantity. So if you sell 10 tickets, that'd be $75. You sell 100 tickets, it'd be $750. That's it. Cost times quantity, that's total money coming from adult tickets. And let's add to that the $5 times every discounted ticket. And together, the total money from both tickets must be greater than or equal to $240. All right, now our instinct might be to solve this for y equals mx plus b to graph it. But if we solve it for y equals mx plus b, we are not going to always get the nicest slope or y-intercept. So it is best to graph word problems using x and y intercepts. X and y intercepts are best for word problems or application problems. It gives you a more accurate graph. And the reason I'm saying it gives you a more accurate graph, if you have a y-intercept that's not a number that we have, if we're counting by tens and your y-intercept is 48, and then you try to do a slope of 4/5, that's not going to be very accurate. So having the x and y-intercept are going to help us. Now I'm going to go ahead and slide this down. We're going to set up our graph, but before I even try to set up my graph, I need to see what kinds of numbers I have. 240 is much more than I need. So we're going to go ahead off here and we're going to talk about our x-intercept. And I know that it's going to be an ordered pair with the y value being 0. And so I take that 0 and I plug it back into my original equation. So 750 times x plus 5 times 0 has to be greater than or equal to 240. So that's going to cancel out. I get 750 or 7.5 x is greater than or equal to 240. Go ahead and divide. And we get x is greater or equal to 32. So we're going to come back and use that, but let's make that our ordered pair of 32, 0. All right, let's take a minute and find our y-intercept. Again, an ordered pair, it's on the y-axis, the x value is 0. Maybe I'll bring my equation down here. Just brought that down, that way I have it in place. Okay, so take the 0 and plug it in. So it'd be 750 times 0 plus 5y greater than or equal to 240. That's gone. 5y greater than or equal to 240. Divide both sides by 5. So I've got y is greater than or equal to 48. All right, so these are the 2 points I need to get to on my graph. And that helps me to know what to count by. So when I go to label my graphs, I am going back up to what my x and my y stood for. So my x-axis is the number of adult tickets and the y is the number of discounted. So I'm going to go ahead and write that down here. This is going to be number of, or amounts of adult tickets. If you defined your variables differently, that's okay. Our graphs would be reversed. And this is number of discounted tickets. Okay, so on my x-axis, I have to get to 32, 0. So if I look, I might take a minute and count, okay, 10, 20, whoa, that's too small. I'm going to go ahead and count by 5. So there's 5, 10. Please make sure you block off that first one. So 5, 10, 15, 20. I don't have to show everything, but each one has to have a block to represent. 35, 40. So make sure you have an even interval. One of the mistakes I see is that people start at 10 and then they count by 5s. Every block has to count by 5 units. If I try to count by 2s on this graph, I think I would have run out of space. All right, I can count however I want to on the y-axis, but it does work out again to count by 5s. So there's 5, 10, 15, 20. Again, each block is 5. I'm just showing every 10. I needed to get to 48, so I am covered. All right, so if you think about this, the x-intercept is at 32, 0. So I'm going to go over, and I'm estimating here. Here's about 32, 0. There's my x-intercept. But I want to remind you, we were looking at this earlier. When we solved this, we got x was greater than or equal to 32. So if I look at this like a number line, x is greater when I go this way. So I'm going to talk about shading going that way, and I'm going to use that in a minute. The y-intercept is at 0, 48. So it's about here, just under 50. And it says y is greater than 48. So that would be shading up. Now, on a word problem, I have to think about the application here. So normally we would draw a line and it would have arrows going down and arrows going up. But this is a word problem. And if I draw past here and I go up to the left, I now have negative adult tickets being sold. So you actually want to start and stop at your x and y intercepts. So this is going to be a segment. It cannot continue down because then we'd have negative discounted tickets. So you have to think about the meaning of a word problem and not just a regular graph. Now that I have that, I drew a solid line because it could be 240 or more. And so both of these are greater than 200 or greater than 32, greater than 48. And so I would be shading everything above here. So what is the meaning of this? Got a lot of graph to shade in here. The meaning of this is if I get any of these ordered pairs down here, 10 adult tickets and 20 discounted tickets, they won't make that $240 or more to cover their costs. If I get something on the line, that will be exactly $240. And if I get something up here in the shaded region, that means they met their goal of $240 or more. So we've covered our graph, and we want to go back up. There was one more question here. I think I'm going to have to sneak it in right here in this corner. And it says, if 20 discount tickets are sold, how many adult tickets must be sold? Okay, I'm going to go ahead and do this algebraically. So if 20 discounted tickets, that's the y value. So I would have 750 times x plus $5 times the 20 tickets that are discounted is greater than or equal to 240. I'm just putting this in here and solving. So that would be 750x plus 100 is greater than or equal to 240. And then I would subtract the 100. And I get 750x is greater than or equal to 140. Divide both sides. And I would get x is greater than or equal to 18.7. Okay, you cannot leave that answer for several reasons. 1, you can't sell part of a ticket. 2, there's no label. And 3, it's an inequality. So when you go to answer this type of problem to get full credit, you would explain your answer. If 20 discounted tickets are sold, if 20 discounted tickets are sold, then 19, and here it is, or more adult tickets must be sold. So let's talk about that. If you sell 20 discounted tickets, then 19 or more adult tickets must be sold. It was X is greater than or equal to 18.7. So even if it was 18.1, if I round it down to 18, we're not going to make our $240. We're going to be less. So actually, we have to break any rounding rule and always round to the next ticket. But here's the other key. It's just not 19 tickets must be sold. It's 19 or more because it's an inequality. So 19 or more must be sold to make that work. If we wanted to go down to the graph, again, it's not a complete accurate graph since we couldn't count by ones here. But if I looked at 20 discounted tickets, and I went here to 20 discounted tickets, do you see that I'm really close to that 20 there? So 20 discounted tickets right here is about 20, so 18 to 20 tickets. So my answer is reasonable.